All right, so I think we can slowly get started with part two. That will be 1 hour, 1:30 to 2:30 p.m. And I will hand it over to Jacob to discuss about deep operator networks. That will be the topic of part two.
Thank you, Paris. So we're going to now introduce our first example of a parameterized operator learning architecture. And so what we saw at the end of the last code tutorial was the so-called image-to-image regression. And this was the kind of model that I brought up in the introductory slides, where we treat the permeability field for this flow through porous medium example as actually some pixelated image. So we only have measurements along some grid, and we'll just treat that as some kind of picture. And what we want to predict is the flow across this domain, which, since we've discretized it, is just some other picture. And so the image-to-image architecture you saw George present was just this kind of convolutional neural network, effectively, that sort of shrunk the size down with some encoding and then blew it back up with some decoding, but it was fundamentally tied to that discretization in terms of the places of the output that it could predict a value of the flow. And what we're going to see in this section is the first example of an architecture that, at least on the output side, is not going to be tied down to where you're allowed to predict values of the output function. This is going to be an architecture where we'll be able to query the output function at any location that we want as a property of the model itself. There's no interpolation that we do after the fact going on. This is something that the model gives us for free because we're going to derive it from this operator theoretic framework. So to remind everyone, again, just of the problem formulation, we're going to have n pairs of input and output functions. And our goal is to learn an operator actually between the spaces of functions such that it associates each output to an input. So in the example of the Darcy flow, the U's are the permeability of the domain that we're looking a fluid pass through. So this area is more porous, this area is less porous, but there is a value at every location in space. And the output S would be the flow actually through that domain at every point in space as well. So how do we even start coming up with a potential architecture to operate on functions itself? One of the properties that we would like such an architecture to have is a property of universality. And this is an approximation theoretic quality that an architecture might have. And neural networks have this property, which is partially what we attribute their great success to. This was proven in the late 80s, I suppose, and then into the 90s by a couple different methods, but that neural networks are universal function approximators. Everyone, this is important to cite if you're using neural networks or you're saying something theoretical about them, that they can, if they're wide enough and they're deep enough, they can approximate any function. So we would like this property to hold for the operators that we parameterize as well, because nature is giving us some kind of continuous operator. We don't necessarily know what it is, but we want to make sure that our model is rich enough to capture its behavior as long as it's, let's say, continuous or something. So one idea that was proposed in the 90s was an architecture that looks like this. And immediately, I'm sure everyone's eyes glaze over because this is horrible looking. We have 1, 2, 3, 4, 5 different parameters here. There's 3 indices. They claim that this works. Like most machine learning things in the 90s, someone came up with a great idea and everyone forgot about it for 20 years. And now we're using it again. And what was nice about this architecture is that it came with a guarantee of universality. That if these sums are large enough and we tune our parameters accurately, this will be able to approximate any operator from a compact set of functions to a space of continuous functions. We're going to take a step back here, though, and try to motivate how on earth you would come up with something that looks like this from scratch. So to motivate this architecture, we'll draw a little diagram of what our goal is. So our domain is some compact set of functions, which we'll call calligraphic U. And the operator that's out there in nature, corresponding the input functions to the output functions, is going to map this compact set to another set of functions here. And so our goal is, given a single input function, how do we evaluate the corresponding point in the output domain of functions at any point, any query location? for one of those output functions. So in this sense, our goal is really, how do we approximate functions in this set G of calligraphic U? This is a set of functions. And to be able to come up with an operator learning architecture is really to say, we have a way to approximate functions inside this space at any query point in their domain. So this is kind of how we've rephrased our operator learning goal. To try to do this, the first thing that we note is, because we assumed our input set of function was compact and our operator is continuous, this output set of functions itself is also compact, as a compact subset of some infinite dimensional vector space. What's nice about this compactness assumption is that this actually means for any epsilon that we have of how far away to the true functions in here we would want to be, there actually exists a finite dimensional subspace of the output space that is epsilon close to any function in here. What's nice about finite dimensional spaces is that finite dimensional spaces have finite bases. Again, because we're in a function space itself, this basis consists of functions, which we'll denote here by T1 through TD. And we have, we put the argument y there just to remind everyone that they can take any y in that domain, calligraphic y, which is the domain for the output functions. Associated to this basis, then, we have coordinates for any function in this subspace of functions here that we know is epsilon close to the things we want to approximate. It can be represented in this basis with some coordinate functions as well. And because the functions in this output set here come initially from functions in our input domain, the little u's, there's a coordinate for each little u for this finite dimensional space that approximates this space here. So the main point of this very high level sketch of how the Chen and Chen proof works is that because the output, the image of this operator is compact, it's well approximated by a finite dimensional subspace of functions. If we can find the appropriate basis and the appropriate coordinate functions, then this means we have an epsilon approximation actually of the output of our operator. Is this clear? Are there any questions here? So what we've arrived at is that this is a reasonable architecture to propose for an operator learning model. These are functions which represent a basis of a subspace that approximates the image of the operator, and these are the associated coordinate functions. So we have to find a way to come up with an architecture now for these two pieces. We need some functions that will take our input and return real numbers for us. And we need some functions that will take the output query and also return real numbers for us. So there's one question. Did you say that the B form basis? So the functions tk are forming a basis. So this lies in a space of functions from y to, let's say, r for now, to keep things simple. So a basis of a finite dimensional subspace of this space of functions will be a collection of functions from y to r. The coordinates for a single point in this set then will depend on the point that it came from, which is why we write them as functions of u. So you should think about the b's as coordinate functions and the t's as basis functions for this approximating subspace. Two other questions. Yes, so the b's are more like coefficients. And answer these in order. In practice, will we be able to assume the domain is compact? So this is an assumption that is made very much for the convenience of these kinds of theoretical statements that we can make. Of course, in practice, we don't necessarily know that we are really dealing with a compact input space of functions, but there are extensions to these arguments that can give up the compactness assumption and also the continuity of G if we instead say that G is measurable and the operator itself is in L2 with respect to some measures on the input space. In those cases, then you can reduce everything back to the compact scenario by approximating things from the inside with compact sets, you end up with an extra epsilon that you carry around, but the arguments can go through. Do we require the basis T to be orthogonal? No, we do not. Any other questions? Okay, so we've arrived at this general form, again, where this is a basis, and these are a sort of set of coefficients for this basis. And now we need to choose actually how to form these functions and functionals. Because we're doing machine learning, the answer is, of course, let's use neural networks. So what the Chen and Chen architecture proposes is we'll approximate this functional, which again takes our input function u and maps it to a single real number by taking m measurement points, which are sometimes known as sensor locations, and pushing them through a single layer neural network. Pick your favorite activation function that gives a universal class of neural networks. Sometimes these are called Tauber-Wiener functions. And this is just your typical one hidden layer MLP. Then we will do exactly a similar thing with these basis functions that we want to learn, the TK. We'll form them as just a very, very simple neural network. And this actually is exactly this architecture, broken into pieces. So this is the term here that represents what's sometimes known as the branch network. This is mapping our input function u to the sort of coefficients that correspond to it. And these are our basis functions for our approximating subspace of the output. And we put it all together, and we have this proposed architecture that depends on these parameters C and these here as well. And so here's a diagram of the kind of forward pass of this model. The input function goes in, we measure it along some locations, it gets pushed through its component to get our coefficients. We take our query location, this is the place where we want to evaluate the output function at in its domain. We get the value of those basis functions at that output query. And then we effectively take the dot product of these two things to get our answer for the operator. What's really nice about this architecture is that we've made no assumptions on where in the output domain this query Y is coming from. So whereas in the image-to-image architecture that we saw in the previous code tutorial, we were only ever allowed to query output function values, the flow through that material along the grid that we had initially set up. But here, because we reasoned about this as a subset of the function space, and we found some basis of functions for it, if we've by modeling this way, we can evaluate it at any point Y that we would want. So in theory, we could get the finest resolution that we want for the output, assuming that the model was trained well enough. Check for questions. So this was all totally formulated in the mid-90s. And again, they were able to give with this guarantee of universality. And so this is saying if our domains calligraphic X and calligraphic Y for the input and output functions respectively are compact, and the domain of our operator is also compact, then for any accuracy that we would want, there exists a model of this form such that we're within epsilon close to the true operator in the supremum norm. So as we discussed before, the compactness assumption on the domain of the operator calligraphic G is important to do these finite-dimensional subspace approximations that give us a basis. The compactness assumptions on calligraphic X and Y are to ensure that using neural networks for those functions B and T themselves are expressive enough. So in proving this, it really reduces to the universal approximation property of one-layer neural networks themselves. And what allows us to make that transition is having the compactness in the domain of our operator calligraphic G. So at the end of the day, a lot of these architectures, inherit their universal approximation power from the approximation power of the components that we use to build them. And if you look up a lot of the proofs of this and other architectures that we'll talk about, at some point they will be appealing to the universal approximation property of neural networks. And a lot of the work is in translating your approximation problem from the operator scenario down to the neural network scenario, effectively. Are there any questions here? Okay. So now we arrive at the DeepONet. Everything we've talked about, as I said before, happened in the mid-90s. And so this paper was rediscovered by some folks at Brown. And they said, this is a great idea. This is exactly what we need. We need a universal approximation property. But now we have the tools of modern deep learning. We have the compute power. We know that deep architectures are very effective. So let's take this idea and instead replace our single layer branch and trunk networks with deep neural networks. They could be convolutional, they could be MLPs, but we know that these things train well. And this should, in theory, give us a very, very powerful form of an architecture for learning operators. And they additionally were able to extend and give a alternate version of the universal approximation theorem inspired by Chen and Chen, but now applied to this deep branch and trunk network scenario. And thus, they call it the DeepONet. So something to note about this is that while the input sensor locations will be fixed, again, the output query location can be anything. So you could get a resolution, as fine as you want for the output points. I will hand it over to Paris now to talk about kind of how we train this in practice and some very interesting applications of what this architecture allows you to do.
Great. Thank you, Jacob. Sharing my screen. I see there's also a question perhaps we can address, or I can take it in this slide. All right, let's see. So let me switch the slideshow. Right, so now that Jacob described the basic architecture and its properties, let's see how we can actually formulate a supervised operator learning problem and use the DeepONet architecture to solve it. So, of course, we are in the supervised setting. So what we require here is paired observations of inputs and outputs. So input functions are, as you see in the sketch on the top left, we have collection of examples, different input functions, and then their corresponding output functions. Now, typically, the input functions are represented in this architecture by means of point-wise evaluation, so a set of measurements at locations x1 to xm. Typically, we refer to these as the sensor locations. And typically, in this architecture, these locations will be fixed across all examples in the input function space. Correspondingly, we will have also measurements, observations of the output functions, but those need not be fixed. Those could be at any continuous location. And in fact, we would have a different number of measurements across the different examples in the data set. As you see here in the sketch, in this first curve, we have two measurements indicated by the black dots, but the next example, maybe we only have one measurement. So putting it all together, a training data set for training a DeepONet model basically consists of a triplet of input functions evaluated at a set of sensor locations, corresponding query points where the output measurements are evaluated, and then the corresponding values of those output measurements. So if you see the top right of the slide, we have basically exactly this organization of a training data set. We have input function examples, we have corresponding query locations, y1 to yn, and then the measurements of the output functions evaluated at those locations. Having this structure into play, and basically this is the only kind of challenging part from an implementation point of view. Basically, how do you structure your training data set to this format? Once you do that, then the training becomes trivial. You can typically employ the empirical risk minimization, formulate a mean square error loss, as you see in the bottom of the slide. And that will allow you to train all the tunable parameters in this model. That will be all the weights and the biases in your branch and your trunk networks. So you just evaluate this loss function, which is a function of the trainable parameters, and then you backpropagate to update those parameters iteratively within your favorite gradient descent optimizer. So that sort of summarizes sort of the structure of the training data and how those are propagated through the model and how basically the training works. So let me just walk you through some simple examples just to illustrate the capabilities of this framework, starting from a pedagogical example that involves predicting a trajectory of a simple ODE system. So as you see in the top left, we are given some ODE subject to some forcing term U of X. And now our goal is to build a DeepONet model that can predict the trajectory of the system for any given input function U. So during training, what we will do is basically we will generate a collection of input functions U, perhaps by just sampling a Gaussian random field. And then we will take those input functions, we will plug them into some ODE solver, a classical numerical ODE solver, to obtain the corresponding trajectories S of X. And now that gives us access to a collection of examples of paired input-output examples. That will be our training set for training the DeepONet model. The goal of the DeepONet model is essentially to learn the antiderivative operator that you see on the top right that maps inputs U of X to output trajectories S of X. Now the model can be trained, and once the model is trained, in an online stage, the user can provide a new input function, U of X, hopefully originating from the same distribution of input functions that were used during training. And then the DeepONet model will actually be able to readily predict the entire trajectory within a simple forward evaluation. So you see here 3 examples. These are examples from the test data set where U of X takes the form of X, sine pi X, and sorry, let me see, what's the other one? I have my, and then sine 2 pi X. And then the DeepONet model can accurately predict those 3 trajectories. And again, here the catch is that obviously the test input functions come from a similar distribution as the input functions used for training. So essentially the model is still operating within an interpolatory regime. Now the benefits of doing so are not so evident in this simple example where you might say that the integrator for solving this problem is really, really fast and we don't, there's no need for a surrogate model. But this is just an illustration. In the next few slides, I'm going to show a few applications where actually the underlying classical numerical methods can get quite expensive, whereas the DeepONet, after it has been trained, it can actually introduce very significant speedups in predicting the evolution of dynamical systems. So I'm borrowing here some applications that Georgios Kissas was kind enough to share with me, and he actually gave a talk 2 days ago in this workshop highlighting some of those applications, just to give you a sense of the capabilities of the framework and the type of problems that it can handle so far. So starting here, we see a simulation of an electroconvection system. So this is a fluid flow simulation that is coupled to an electric field. So you see, for those of you familiar with this type of problems, you see a set of equations on the left-hand side, which is the Navier-Stokes equations, describing the fluid velocity U and the pressure P, subject to some external forcing F. And this system is coupled, the fluid system is coupled with an electric potential phi that governs essentially the evolution of cations and anions for the system, which is a C plus and C minus that are evolved according to some flux J. Now, the question at hand is, could we actually build an operator learning system that can predict C plus, C minus, and the 2 velocity components of the fluid for any given electric potential that is provided as an input? So as you see in the bottom left, the goal here would be to build actually 4 distinct DeepONet models to predict C plus, C minus, U, and V for any given input function phi of X and Y. Now, to build this model in a data-driven way, obviously first one needs to construct a training data set. And for that, the folks at Brown run conventional CFD simulations using the spectral element method to create training data across several different examples, several different cases. Each case corresponds to a different electric potential. And then once this training data has been generated, a DeepONet, or actually in this case, 4 different DeepONet models can be trained in order to learn the mappings that you see on the left-hand side. Now, once those models have been trained successfully, then at test time, they can be used very, very efficiently to compute the quantities of interest here for any given new potential function. So now at test time, if you were to compare the runtime of a DeepONet, which is about 0.1 second on a single GPU, versus the runtime of a conventional CFD workflow that would take hours on a parallel computer, you would see a speed up of the order of 10 to the power 4. So you have like a very significant four orders of magnitude speed up in terms of the efficiency and the runtime for computing these output fields of interest. And of course, there's going to be some approximation error, but it turns out for this particular application, which seems to be simple enough for the DeepONet model to handle, the predictions are quite accurate. Now, moving forward, I would like to motivate a slightly different setting in the next application, which involves phase field modeling of fracture, in which I want to highlight the fact that in many of those systems, on one hand, you may have access to observational data, you may have access to experimental or simulation data, but many of those physical systems are also governed by some underlying physical principles and physical laws, which you also know a priori. In this particular case, you have some laws of plasticity and continuum mechanics. And the interesting observation here is that one can combine the fact of the access to observational data with the underlying physical principles to try to constrain those operator learning models to produce predictions that not only fit the available data, but also satisfy the underlying physical laws. And by doing so, the goal is really here to introduce some notion of data efficiency. So the hope is by leveraging the underlying physical principles, one could train those operator learning models with less training data, which obviously it could be a bottleneck since the cost of data generation for many of those engineering applications could be very large as they involve expensive simulations or experiments in the background. So this is a busy slide. I'm not going to go through the details of the equations used, but really the problem here is that given some initial configuration of a crack in a material, can we predict the time evolution of the crack, of how the crack propagates inside that material? And can we do that by leveraging a set of paired observations of initial crack configurations and their corresponding evolution, alongside with the knowledge of the underlying physical and mechanics laws that describe the evolution of this problem? So again, the bottom line message here, and we will revisit this in part 4 when we talk more about what I call physics-informed DeepONets, is that we can build a DeepONet model, again, to approximate the target quantities of interest, and we can actually constrain this DeepONet model during training in order to produce predictions that satisfy the underlying equations. In this particular case, the equations correspond to some energy balance criterion that is formulated in a variational form, as you see in this slide. So at the end of the day, as you see on the bottom right, we will have a loss function that not only tries to fit the observed data, but also is trying to minimize the residual of the underlying physical law at the same time. So we will revisit this later on at part 4. For now, I'll just leave you with a nice animation. And again, to highlight the fact that the data-driven approach versus this partially physics-informed approach can lead to enhanced data efficiency and also enhanced accuracy. So physics-based constraints can actually really help in this context, and we will revisit this concept later on in part 4 to elucidate some of the details here. What you see again is an animation from the test data set after the DeepONet model has been trained. The user provides an initial crack configuration, and then the model, which corresponds to the phase field formulation of the underlying PDEs, can predict the time evolution of that crack in the material. So that is all for now in terms of the methodological part. Before we head on to the tutorial, let me just briefly mention a few drawbacks of the DeepONet formulation, starting with the fact that the input functions are typically represented by pointwise measurements at a set of sensor locations that need to remain fixed across the different examples in the dataset. So that could be somewhat limiting in certain applications, and that's something that you need to keep in mind. But of course, as we will see later, Pointwise measurements is not the only way one can represent input functions, and there's alternatives such as spectral representations that we will discuss in part 4. Again, I just mentioned that the sensor locations also need to be fixed, not only the number of the sensors, but also their locations. And then finally, if one needs to change those locations or the number of sensor points, he would have to build a new model from scratch and retrain a new model that contains a new branch network that can facilitate this new input function representation with more sensors. So moving forward, we will actually now for the next half an hour focus on implementation aspects and how one can efficiently implement and deploy DeepONets in JAX. And then we'll take a lunch break and move on to part 3 and part 4. Part 3 will be focused on neural operators and Fourier neural operators. And then in part 4, we'll go into more advanced topics such as physics-informed learning and applications. So now I'll just hand it over to George to walk us through the implementation aspects of DeepONets.
Yes, thank you very much. Let me share my screen. Okay. All right. Okay, so DeepONets in JAX. Right, so something that I didn't mention in the previous tutorial is that if you try to do like an image-to-image regression strategy in which you increase the resolution, right? So you increase the resolution for this Darcy flow problem, you will see that the accuracy deteriorates, right, as the resolution increases. You can do that. It's really easy, or you can test it because I have already run these examples and you can just load the parameters, right? So, okay, so let's go, with that said, let's go to see, like have an introduction to how the DeepONet works in JAX and in general, right? So what we will do here is that we will talk about how to implement DeepONet for one query point. Why is that? Because as we said before, JAX has a lot of, has this automatic vectorization capability, right? So if we can write our forward pass for one, right, for one query location, then essentially we can vectorize it and have as many query locations and as many, batches as we want. Okay, so let's start. Okay, so this is like a DeepONet. This is how a DeepONet looks like, right? So, okay, so what is that about, right? So we have an input. So given x in RDX and y, okay, we refer as x in x and y in y as, so x is the input locations, y are the query locations, right? We have some functions that they are these continuous functions that we call u, the input functions, and s we will call the output functions. What is our goal? Our goal is to learn some operator, right, using input-output function pairs, right? So we have u and s pairs, n of those. Using these pairs, we want to learn this operator. Okay, so in order to do that, we consider this parameterized model, like this f. So g in general, we use it as a notation to denote true operator, and f is the approximation. Okay, so t is called the trunk network, and b is called the branch network, respectively. Okay, so let's talk about how this branch and track work, and then we will go over some, we will go over how to construct them and then how to code them. Okay, so the branch network is a function that takes some m by the u inputs. So I think that I'm missing a slide. Sorry. Yeah. Okay, so there's a slide missing. Let me. Oh, sorry for that. But I think that we need that to explain. Anyway, Okay, let's go back to that and give me a second to find it. Okay. Anyway, I'm sorry for the inconvenience. I will try to explain that, and I will upload the tutorial because, yeah, anyway. So M, what are M? M are the evaluations in the input function. So you have M of the input functions, right? And your input function can be scalar or it can be vector, right, for you. For example, if you have like a scalar field, like a pressure or temperature is a scalar, right? And M is the evaluation points. So for example, let's say that you have a grid that is 32 by 32. So on this 32 by 32 grid, you have 1024 evaluations, like M is 1024, right? And then this branch network takes this U, which has this dimension, and then provides you with something that's N by ds. N, you can think about it as your the hidden dimension, right? The size of the hidden dimension. And then ds, you can think about it like the dimensionality of the output. For example, it is like a vector output, it's a velocity, ds can be 2. If it's a scalar field, ds can be 1, right? It depends on this, what's this s, right? So now the trunk network is, as we said here, it takes like a scalar input, right? It takes a y, which is 1 by dy, right? So what is dy? Dy is essentially if your problem is 2D, it's 2. If it's 1D, it's 1. If it's 3D, it's 3, right? So on and so forth. And then it provides you something that's again n by ds, right? So again, n is the dimensionality of your hidden dimension, how large is your hidden dimension, and ds is your output. Okay, so this happens for each square location, and then this will provide you with some output that is s, so 1 by ds, right? So ds again is the dimensionality of your output. Okay, so what you see here in 1 is how you can write this approximation of s for 1 point. Okay, so now we will talk about how to construct this using vectorizations for batches and for multiple y's. So you fetch batches of input-output function pairs, and then you also can fetch batches of y labeled data inside this input output inside this input output pair. Okay, so okay, let's go. You can read the paper from Lulu and Georgios Kissas at Brown, and you can see in this section how they construct this implementation where they split the branch in the track network. This is something similar, right? Okay, so again, let's revisit the problem. We have the same problem as before. This is the flow through porous medium. Okay, now we have some more kind of operator learning language, which is essentially that given some u, what we want to learn is we need to have this solution operator, right? We need to find this solution operator g that will map u essentially to s. Okay, and for this problem that the output and the input domain coincide, you can say that x is equal to y. This should be a y, and then dx dy equals 2. Okay, and the du ds equals 1. Okay, so what we need to find is this, we want to essentially find the solution of it. Okay, and then everything else is defined as before. So we assume that we have some, we have access to some nx by ny measurements on a grid, and then we want to match them to some nx by ny outputs. Okay, the dimension of the output can be arbitrary, it doesn't matter. So introduction to stacks. What is stacks? Stacks is a library that we used in the previous tutorial. That's a JAX library that instead of using objects, like in Torch that you have modules or something like that, to build more complicated forward passes and more complicated, let's say, models, you use essentially pure functions. Okay. So again, in this case, the parameters are not some attribute of the model, that you need to handle them explicitly. Okay. So it's, as before, its model of stacks, of this stacks library is created, it has inside it some initial init function, which is initialize the model, then some forward path that applies the transformation. Okay, so the cool thing about stacks is, as we said before, with that this stack serial function, that we can essentially take different layers and stack them together in serial. So first operation applied, then second operation applied. Also, this creates a new layer, and this layer we can apply these transformations like vectorizations. Okay, and then we can take derivatives of that. For more information, you can check these references. Before going to that, maybe we should take some time and talk about how you handle state jacks. Okay, so how we handle state jacks, because as we said before, jacks are considers pure functions, right? There are no side effects. So how do we have model parameters? How do we manage optimizer states? Okay, so in order to do that, we said that we handle them explicitly. So let's go one step further and talk about it, how they do that with using some tricks from functional programming. Okay, so let's consider that you have this counter example, which is essentially you count from 1 to 3. Okay, this is the idea. And then what you want to do is take this function and essentially JIT it. Why? Because you need to make it faster. Okay, so what we do is take this function, we JIT it, and then run it, right? Like we do here. See what you get? We get 1, 1, 1. This doesn't work. Why doesn't it work? Because if you see here, you have some state, right, which you update. And if you try to update this state, you cannot, because as we talked about in the first tutorial, impure functions do not translate to the intermediate language XPR. Okay, so we need to find a way to essentially, make this work, because we handle states in the machine learning. We handle parameters. Okay, so an easy way to fix that is that you can essentially not only you can create essentially functions that not only provide you with the value of the operation, but also provide you back with the state. Okay, so let's say this: we create a new counter that also creates the value and creates the state. Obviously, this is like a pedagogical example. Okay, so these things are the same. So now, if you try to do that, then you see you get 1, 2, 3, 4, 1, 2, 3. Now let's try to JIT it. Let's see what happens if we JIT it. If you JIT it, then you will get again 1, 2, 3, which is the correct answer. Why is that? Because we need to handle the states explicitly such that they can translate to XPR. Okay. Okay, so let's start talking about DeepONets. Okay, so the first thing that we need to do is that we need to start importing some libraries that we need to use in order to implement it. As you can see, I have this OS environment pre-allocation. This happens because when you run JAX in your GPU, then it pre-allocates 90% of the memory of the GPU. And then if you want to load some data on the GPU and your GPU memory is not big enough, then what happens is that you can have some error, right? So this is such that you do not pre-allocate 9% of the GPU memory. It's not needed, you can remove it. I put it here such that we can essentially, make, if you want to make predictions that the NX and Y are large, then that means that you don't come to some memory issues. Okay, so randomly choosing output labels for training. Okay, in this case, now what we talked about before, you can have in the DeepONet formalization, you have some input function and some output functions. Your input function location should be fixed, but your output function location can be random. So for functions pairs U and S, what you can have is U for each function pair evaluated at some x's and S evaluated at some points big M. Out of the points big M, you can randomly choose P, right? Out of them, you can randomly choose P. P can be different. So these points can be different for each realization. It doesn't matter. Okay, so the thing is that if you do that in this implementation that we are talking about right now, you cannot have a different. You have a fixed number of P outputs for each input function, output function pairs. We did that because if we have this, if we make this assumption, we can make the code faster. But there are more general implementations which you don't need to consider that. Okay, so let's go for that. When we want to sample P points, essentially we use this function. What does this do? It has some random numbers, it creates random numbers, and then by using this random numbers x and y, it just samples, some locations and some outputs, right? Because we need the outputs and the locations, right? The locations, we need some particular locations and the outputs for this particular location, such that the locations go to the DeepONet, the outputs we use them for the loss. Okay, so again, now what we want to do is handle batches. As we did before, in order to fetch mini batches, we create this class, and this class, what it has is essentially two items, right? One is something that takes an initial key and splits it each time that we call this function, and then another thing, it's essentially that provides us with batches. Okay. Now we will employ something else that is called harmonic feature expansion, and it's from this paper that you can read. The harmonic feature expansion essentially is something like an encoding, like a positional encoding in transformers or in this attention literature, right? Which is essentially, it's instead of having some in the transformers literature, is instead of having some positional information, because you can do that especially with words, what you have is an indirect positional information about some functions that have to do with how other functions affect them when they are applied. Okay, so in the physics world, that means that if you have this harmonic feature expansion in mind, you can take it's an intuitive way to handle some structure inside your data set, like periodic boundary conditions, oscillations, high frequencies. Because let's say for oscillations, you can choose some frequencies such that you normalize your output based on those frequencies, this has been shown to be very effective, right, in training. The result is much better, the accuracy. So how do we do that? So we have a harmonic feature function expansion for y, which is the query locations, and for u, which is especially the input functions. So we do that in two ways. This is a vectorized way to do it, right? So essentially we create two arrays, right? And then we provide the vector of the input location, of the output locations, and then essentially we take the first and the second dimension of that, because it's two-dimensional, right? We create some tilings here such that the vectorization would work, and then we apply with essentially this to 0 pi to 1 pi. This is a vector-wise way to do that. And then we have this index of date, which is, if you remember, we have these device arrays that they are mutable. You cannot essentially change their values. So we use these functions such that we can essentially change their values in a vectorized manner, right? And this is pretty much very close to how you do positional encoding in transformers. Okay, and we do that for y, we do the same thing for u. Okay, right. So now let's look for the loss function. The loss function in this particular example is this what we call relative L2 loss. This was the people from Caltech at Fourier neural operators were using that, and this is, you will see that in the next tutorial, right? And we will use the same thing. And this is essentially a good way to weight your loss function independently, right? Based on on the target function, right? So this, by using that, you avoid biasing your neural network, your learning towards like larger magnitude solutions, or and you can essentially have better results because of this individual weighting of the loss function components. Okay, and this is how you write this loss, is essentially an object, and then what you have here is this L2 relative norm. Okay, relative L2 error, let's say. Right, so the DeepONet model implementation. In order to do that, we define the branch network and the trunk network, which is essentially, again, two stacks functions, these pure functions. And then here, this is the most important part, in my opinion. It's what, as we said before, we defined the forward pass of the model for one query output location, for one Y. So what we're doing here is that, as we said before, when you are initializing your stacks model, you need to provide some shapes for the parameters. If you provide this -1 here, what it does is essentially it says, okay, don't think about the batch dimension, don't think about the first dimension, which is how many output locations do you have. Okay, so vectorize on both of them. So if you provide something that it's 100 by 10 by 3, it will take the first out of 3, and then the second, the third, so, and then all the batch. So it vectorizes in both dimensions. So this is cool because this provides us with additional functionality, and this provides us also with the what we can do with that is that we can have one shot, right? Super resolution. We can predict 100, 2,000, 5,000, output locations at once. That's pretty much the idea, and this is why this is cool, and this is some functionality of stacks. Okay, so let's see how this model works. So the DeepONet takes the parameters because you have, again, the state to be explicit. It takes some inputs like the U and the Y. And then what it does has a trunk network and the branch network. And then what you see here is essentially a way to do the above operation for batches, for many input-output pairs, and for many output locations at the same time. So I believe that this is, it's written like that, such that it's fast, but this is pretty much the idea, because this, the stacks vectorizes it, so it takes one output location at its time, and then for one output location, it has this N by ds that you saw up here, right? This N by ds. So what it does is the second part, the two last dimensions, do this N by ds. This is for the branch, and then for the trunk, the same. So now we have two additional dimensions, one for the batch and one for many output locations, right? So this is why this is a the matrix that has 4 parts. Okay, and then this is happening with einsums. So you do these operations using einsums such that they're fast. So this reshapes is in order to do the operations above, as we said, for many batches and P locations, and then you just einsum them and have batches of outputs. Instead of having one location at the same time, you have a lot of them. So that means, what does it mean in practice? What it means in practice is that you don't need to have this DeepONet input structure, these triplets, but there are a lot of U's, one Y, and then the output, right? You don't need to tile the U's in this implementation. So if you don't need to tile the U's in this implementation, there are less memory requirements and it's faster. That's pretty much it. So what you see here is what we talked about before, above. And then this is the parameters, we define the loss. This is the optimizer, it's exactly the same as the previous example. You have a way to get the parameters, the state of the optimizer, way to update, and way to initialize. And this is the stacks module. You see, so what we have done is we define some module in this layer, and then we provide it to the serial. So these operations are done one at a time, right? We define one of those for the trunk network, one of those for the branch network. So in this way, we build these two things. Okay. Now we have the loss, which is what we talked about before. And then we have this step, which works exactly as the step in the previous tutorial. And then we have the train model, right? Which essentially has this loss, the loss train, the loss test. Also, this provides us with the L2 error as we train to see how well the model does. Okay. And then also we have a way to predict the parameters, the train parameters, and we predict the test parameters. These are different because in this paper, the FIR data for DeepONet, they essentially normalize the outputs. So that's why we have one prediction and one loss and one L2 error for each. But you can discard it, it doesn't matter. So we have two helper functions. One helper function that is a predict function. What it does is this predicts, as I said before, you have some big M points in the output, and out of those you choose P, right, to train the model. So what this function does is essentially that you provide all big M points, and then this at one shot provides you back the answer, right? And then the other function that we have is one error, how you measure the error, one relative L2 error for each input-output function pair. And this is this provides you with some statistics, mean, max, standard deviation, right, and minimum. Okay, so this is the main part. The main part is essentially constructed as it was constructed before, right? We need to load the data, and then we need to have some, we need to load the data, and then we need to parse them such that we choose some random P's from the output. And then what we need to do is essentially we need to transform this NumPy arrays now to device arrays. And then we need to reshape them because we have some particular shapes, as we talked before. We have something that needs to be M by du and something that needs 1 by dy. As we talked about, this is the branch input, this is the trunk input, but now we can have P of those because we are doing that in a vectorized way. Okay, so now we applied the harmonic feature expansion, which is essentially what we talked about before, adding some essentially frequencies in the input functions and then some frequencies in the queries. And then now you can normalize the output labels if you want. If you don't use the relative L2 error, it's better to normalize them. If you use this relative L2 error loss function, it's not necessary, okay? Because essentially what it does is that it provides weights for each different part of the loss. Now, what we need to do is provide this data generator, this structure, this class that handles mini batches with the U's and then the Y's and the S. Why is that? Because we need the U's to go in the branch, the Y's to go in the trunk, and the S to go in the loss function, right? So this chooses mini batches for training and then for testing. This test here is pretty much validation, right? So as the model runs, this provides us with this training set accuracy, and then this test set, which is also validation during training. And then this is how we set up the model, like the model architecture. You see that there are some more parameters here as we did before, because it's not exactly M, it's not exactly du, because the du now is enhanced because there is some the feature expansion, right? So the feature expansion is presented by HU. So you have, let's say, 2 features, then you have one, it's a scalar, your input function, so it's 1 plus 2, so it's now 3, right? Because you have 2 features. And this model can be trained using this function. It's actually extremely fast. DeepONet is extremely fast, right? It trains in 1 minute, and then it provides you with 0.7% accuracy for its dataset on the whole domain. And this vectorization thing, I think for me it's cool because now I will show you 2 things. One is I take batches, right? I trained, let's say, in 128, P equals 128. So I have 128 of the output locations, right? And then I have 1024, my big M is 1024, my P is 128. So I can use batches to reach big M. I need, let's say, I don't know, 8 of them or something like that, or I can do it one shot. So with one call of the forward pass, I can predict for as many batches, as many input-output function pairs, as many resolution, and as big S, right? So as you can see, these two things provide exactly the same accuracy. And this is for me to motivate the use of stacks, right? Because this we do like for one Y and then vectorize in 2 dimensions, this can provide with this the exact benefit of one-shot prediction of large resolution in the output as you want. So this could be 100, this could be 2,000, this can be 100,000. It doesn't matter. You can do it in one shot, as long as your GPU can fit it in, right? This is pretty much the idea. And the last thing is, this is one prediction. So this is one input, this is one output, the prediction for one output. And this is how you save parameters. And that is the end of the second tutorial. Thank you.
Great, we're just on time for the lunch break. Perhaps we can take a few minutes just for questions. I know there was a question that I missed earlier. Isn't it a problem that the input locations are fixed for DeepONets? Indeed, it could be in some applications. In many applications, it turns out that it's not, because the structure of the input functions, we have the freedom to evaluate them in terms of the problem setup. We assume we have a collection of input functions, and then it's our choice where we can evaluate them. So if that's the case, we can evaluate them at a fixed set of sensor locations, and that is not a problem. But if the structure of the input functions is dictated by the actual experiment that generates the data, and maybe we have different number of measurements across different examples, that will be a problem for the DeepONet. However, there is alternative ways of encoding input functions instead of just taking point-wise measurements, and we'll discuss more on that on part 4. So I hope that answers the question. Any more questions on DeepONets? And of course, if anything comes up later, please send us an email. If you find any bugs in our code that we're sharing, let us know and we'll fix it. But if there's no more questions, perhaps we can take a lunch break and resume in the afternoon.
So we are starting at 2 p.m. Paris.
Let me confirm. We are starting 2:30.
2:30. Okay.
So yeah, we will have part 3, which is 1 hour long, 2:30 to 3:30 on neural operators. We'll take a quick break, and then part 4 will be 3:45 to 5 p.m. on the advanced topics, applications, and the general discussion. There's one question. Oops, I think. Let's see. How does DeepONet behave with finite-dimensional operators, specifically if you specify a much bigger trunk structure than necessary?
Oh, so okay. So if you mean that if it's accurate or not, I would say that the accuracy. So some part of the accuracy depends on how many input function samples do you have, right? So if you want to do super resolution, so you want to predict more than you have trained, this is what you actually do, right? You have 100 points, let's say, to train, and then you predict for 1,000. I mean, much bigger trunk structure. Do you mean so if it's the structure of the architecture it's much larger, or if your output resolution is much larger than the input resolution?
I think the question might also be referring to, like, let's say the image of the operator actually is contained in a finite dimensional subspace, and I approximate it with a basis that's much larger than needed.
Yeah,
So
that's my understanding too.
London. Yes.
Okay.
So yeah, we haven't. Yeah, exactly. So yeah, for the basis that those T functions represent is I have 100 of them, and the image of the operator actually lies in a 3-dimensional subspace, so they're incredibly redundant. So you might hope that a lot of them are set to 0 or somehow that it finds some redundant solution within that basis. We haven't, I have not at least run any experiments with a scenario like that. I would imagine that what might happen is, in a case like that, you have a lot of solutions then to approximating the truth, because I mean, it's very much not unique in that case. There are many ways to use the over-complete basis to represent the same function. So you would hope, I guess this kind of goes both ways, and then it brings up considerations of actually how is the model trained and what sort of solutions do first order optimization methods find. This is introducing many more global minima in some sense to the parameterization of the model. So it's possible that that helps the optimization, but depending on the structure of the landscape, I guess it also could introduce more suboptimal critical points, saddle points between these things where it might be stuck at. So I'm not entirely sure. On the other hand, if you know that this really is some kind of finite dimensional operator, then perhaps this isn't the architecture that you would want to be using in the first place, and simpler choices might work just as well anyway.
Yeah, and the other thing, from a deep learning point of view, larger architecture will lead to more parameters, and obviously that has to be considered relative to the size of the training data, avoid overfitting issues, and practical trainability aspects. But yeah, I think Jacob's answer covers it. What does out of distribution really mean for DeepONet? Well, I think that relates to the distribution of that generated the functions used during training. And you can imagine that examples that are provided to the model at test time could originate from a different distribution. And that would be an out of distribution example. For instance, perhaps your input functions were generated during training from a Gaussian random field with a length scale of 0.1, but then during test time, you're providing input functions that are generated from a Gaussian random field with a length scale parameter of 10 to the minus 3 or something. And then you would expect, since the model has not seen functions like that during training, it will probably perform poorly at test time, because those examples are basically out of distribution. All right, I think we can conclude, so we can take a lunch break, and then we'll be back at 2:30. So thank you, everyone.
Thank you.